This video serves as a comprehensive review for ME 2040 circuit analysis for mechanical engineers. Our midterm exam have already covered the first 3 chapters. In chapter 1, we learned the basic concepts. In chapter 2, we learned resistive circuits. And in chapter 3, we learned nodal and loop analysis techniques. So this final review focuses more the following 4 chapters. Chapter 4, operational amplifiers. Chapter 5, additional analysis techniques. And chapter 6, capacitance and inductance. And chapter 7, first order transient circuit. So these will be covered in the final exam. And we also know that final exam will be a 2-hour exam. So we will have 5 multiple choice problems and 4 calculation problems. And the multiple choice problem have 2 points each, and the calculation problem is 10 points each. In total, this exam have 50 points. Let's also talk about the notation that we're going to use for the review. The check mark is used to represent the objectives of lower requirement. These are mostly the concepts. And we're going to use a triangle to represent the objectives of a medium requirement. And a star represent the objectives of a higher requirement. These 2 types are mostly in the multiple choice problems. These are more tested in calculation problems. Let's look at these chapters one by one. Chapter 4, we learn operational amplifiers. There are in total 4 module objectives. The first one is the model for op-amp device. We know that there are in total 3 models we have learned. The first one is the ideal op-amp model. The second one is a semi-ideal model. And the third one is a linear model. And of course, the ideal op-amp model, that's the one that is used most often. You're required to know the difference between the 3 models. So in ideal model, it implies that V plus Z is equal to V minus, and at the same time I plus Z is equal to I minus, Z is equal to 0. In class, we had a practice of using all these 3 models, but with the main focus on the application of ideal op-amp model. And we'll be able to use the ideal op-amp model to analyze a variety of circuits that employ op-amps. And this is tied with different applications of op-amps. So in terms of application, we had several examples. The first one is called a unit gain buffer or voltage follower. The second one is the basic amplification of a signal. We also learned the amplification of the difference of 2 signals. And we also learned the summation and the subtraction of signals. And when it comes to chapter 6, we also learn how to add a capacitor into a circuit, make it be able to calculate the integration and time derivative. And the other thing implies it will be tested together with chapter 6. And to tell the application, this is of our lower requirement. We already mentioned all the applications. And the last one is the design op-amp. So design of op-amp, it will be of higher requirement. Also in class, we had a couple examples on how to design. So basically, it follows a 3-step process. The first step is to come with a possible design. The second step is to derive the design equation. Once you come with the design equation, you can compare with the goal to come up with a relationship or is a constraint. Following that, the last step is to select proper resistors that will meet the requirement. Although this is of a high requirement, it's hard to be evaluated through the exam, so this won't be on the exam. Let's look at chapter 5. Chapter 5 focuses on additional analysis techniques. So the first objective is to understand the concept of linearity and equivalence. So these are basic concepts. So mathematically, linearity means the relationship satisfies superposition. And superposition includes 2 requirements or 2 properties. The first one is called scalability. Scalability means if you have a signal U that will generate an output Y, and if you scale the input signal U by 5 times, and the output will be also scaled by 5 times, it will become 5Y. The second property is called additivity. Additivity means the output of a summation of 2 signals that will be equal to the summation of the 2 outputs from the 2 individual inputs. Following that, we learned how to analyze the circuit using the principle of superposition, which is of a high requirement. So in solving problems using superposition, we decompose one problem into several sub-problems, which each has one independent power supply. For example, in a problem, if you have a 3 power supply and the output, say V0, that is equal to V0 part 1 plus V0 part 2 plus V0 part 3. And V0 1, V0 2, V0 3 are the output caused by the first power supply, second power supply, and the third power supply, respectively. The next is to calculate a Thevenin equivalent circuit for a linear circuit. So this will be of a higher requirement. And over here, we learn several different special cases. The first case, where you only have independent power supplies, where you can find a VOC first, then find RTH by setting off all the power supply to be 0, and then look at the resistor of the resistor network. The second special case is for circuits with only dependent power sources, and this circuit that cannot self-start. You need to add a power supply for the calculation supply to find RTH. And in this case, VTH, that is simply equal to 0. And the third case, that's a general case. And in this case, you need to find VOC, find ISC, so that you can find a Thevenin equivalent circuit. VTH is equal to VOC, and at the same time RTH, that is equal to VOC over ISC. ISC stands for short circuit current. So these are the 3 different cases. So once you find a Thevenin equivalent, you can convert that to a Nortan equivalent. Actually, these two together, that leads to another module objective, is to use power source transformation to solve problems. Power source transformation method is derived from the equivalence between Nortan equivalent and the Thevenin equivalent. So where we have a Thevenin equivalent like this, and that can be converted to Nortan equivalent with one current source ISC in parallel with a resistor. This resistor called a Nortan equivalent resistor, Rn. And if that holds, it implies that RTH, that is equal to Rn, that is equal to R, and at the same time VTH, that is equal to ISC times R, so that you can convert one type of power supply to another. And towards the end, when we can simplify part of circuit to be Thevenin equivalent, and we can calculate the requirement for the load, such as the load can have a maximum power. This is the load RL, this is RTH. We know that if it's a load resistor RL that is equal to RTH, it will have a maximum power delivered to RL. And the maximum power consumed by RL, that is equal to PL max, that is equal to, we can use the way how we calculate the power of the resistor for this, so that will be V squared over R. Since the two resistors are the same, so the voltage on RL, that becomes half VTH squared over RTH. And we also know that to use maximum power transfer theorem, we have to find a Thevenin equivalent circuit. So this will be tested together with bullet point 3. So let's look at chapter 6. Chapter 6 talks about capacitance and inductance. The first module objective is to use the circuit models for inductors and capacitors to calculate voltage, current, and power. So these are basic concepts. So you need to know the definition of a capacitance and inductance. At the same time, the calculation involved. So you just need to know the basic 2 equations for inductors and capacitors. And for capacitor, we know that current going through the capacitor. We know the voltage, the current going through the capacitor, that is equal to C times dVc dt. And for inductor, the voltage on the inductor, that is equal to L dIL dt. Then with the knowledge that we learned from chapter 2, you can calculate the rest. So for example, you can calculate the voltage by doing the integration, and then comply with that, you can further calculate the power, and then you calculate the energy stored. And similarly, from here you can do the integration to calculate the current going through the inductor if the waveform of a VL that is given. And further you can calculate power and also the energy stored in the device. So all this relationship has been summarized on one page in the lecture notes. So you can review that page for more details. Over there we also explain the dual relationship between capacitors and inductors. The second module objective that is to be able to calculate the stored energy for capacitors and inductors. Calculation by itself, this will be of a higher requirement, but since these calculations are directly built upon the basic concepts, so we listed it as a lower requirement. And the third module objective is to calculate the voltage and currents for capacitors and inductors in electrical circuits with DC sources. So this knowledge actually is tested in chapter 7, where we need to calculate a steady state value. And in steady state, the inductor works as a wire. And in steady state, the capacitor works as an open circuit. And in steady state for the inductor, you can also see it as a shorted circuit. And the next object is to combine the capacitors and inductors in series and in parallel. So we learn how to simplify a resistor network for capacitors and inductors. For capacitors, if we have two capacitors in series, and we know that the overall capacitance 1 over Ct that is equal to 1 over C1 plus 1 over C2, or Ct that is equal to C1 times C2 over C1 plus C2. And for capacitors in parallel, we know that Ct that is equal to C1 plus C2. And for inductors, you have two inductors in series and a total inductance that is equal to L1 plus L2. And if you have an inductor in parallel, and we know that 1 over Lt that is equal to 1 plus over L1 plus 1 over L2, or Lt that is equal to L1 times L2 over L1 plus L2. So these are the rules to simplify capacitor and inductor networks. Module Objective 5, to analyze op-amp circuits with capacitors and inductors. So this will be tested together with chapter 4. Chapter 7, where we learn the first order transient circuit. The first object is to calculate the initial value for inductor currents and capacitor voltage in transient circuits. So this will be a lower requirement. This is one step towards finding the transient behavior of the circuit. And over here, we need to use the continuity properties. And for capacitor, we know the voltage that is continuous. So VC0 plus that is equal to VC0 minus. And for inductor, the current that is continuous. So IL0 plus that is equal to IL0 minus. The second module objective is to determine the voltage and current in first order transient circuit using differential equation and step-by-step methods. So this will be of a higher requirement. So although in class we learned 3 different methods in total, the first one is called a differential equation method. The second one is called a step-by-step method. And the third one is a Thevenin equivalent method. These 3 different methods are internally related, and the step-by-step method is more straightforward, and it's built upon the result to the differential equation tau times dy dt plus y that is equal to f. It has a solution of yt that is k1 plus k2 times e to the power of negative t over tau. Step-by-step methods is to find k1, k2, and tau one by one. So step-by-step method is composed of 5 steps. So step 1 is for t that is equal to 0 minus, find Vc 0 minus or IL 0 minus. And these are in steady state. And step 2 is to find the initial condition. And the initial condition is built upon the continuity property for inductors or capacitors. When we find the initial condition, it will give us K1 plus K2 that leads to this initial condition. And step 3 to find a steady state value, which will give us K1. And step 4 is to find a time constant tau, and the time constant tau that is defined by using the conclusion from Thevenin equivalent method, where it says tau that is equal to RTh times C for a circuit with a capacitor, or tau that is equal to L over RTh for a circuit with an inductor. Step 5 is to draw the conclusion, the final answer, whatever we are looking for, that is equal to K1 plus K2 times e to the power of negative t over tau for time t that is greater than 0. So this is a step-by-step method. So although we learned 3 different methods, so in the exam, we're going to require you to use step-by-step method to solve it. That concludes the review.